So we've been talking about Pythagorean's theorem for the last couple quests here, and we've been looking at this case. If you look over here, a squared plus b squared equals c squared. And we say that this is a relationship of how if we know two sides of a right triangle, then we can use this equation to help us find the third side. Again, this formula comes from Pythagorean's theorem talking about equal area, or similar area, excuse me, of squares, for example, that side lengths are the sides of the triangle. And Pythagorean's theorem says that the area of the two smaller squares that are based off the two shorter legs of the right triangle, if you add up their area, then it's going to equal the area of the longer side, the hypotenuse, in a right triangle. Right? And so we could solve that algebraically. We could just look at this picture here and use geometry to reason that as well. But the next logical question becomes, well, what if, a squared plus b squared, what if it's not equal to c squared? So then we have to ask what that means, right? So if they're not equal, then what are the other cases? What could happen, right? So let's talk about equations and let's talk about inequalities. Okay, so some examples of equations here. We have just statements here. It's telling us equality. 5 is equal to 5. That's a true statement. We use that in logic quite a bit. We've seen equations that look like this for sure, and we have to solve for x, right? So we have algebraic steps to get this value, but basically we can just look at this and say, all right, well, this expression, whenever you take a number, you multiply by 2 and take 1 away from it, is going to equal some number, in this case 7. Then what is that x value? What number do you double and take away 1, right? Like 4. If you double 4, we get 8, and you take away 1, it's 7, so x has to be 4. Right? So you could think about it logically as well. It's just an equal. When does this expression equal some value? Equations like this, we can talk about the measure of an angle. This is how we denote angles, right? The measure means the actual degree value, the value of the angle. How big is it? 60 degrees, 72 degrees. So it can be equal to another angle's measure. And then this statement tells us then, if two angles have the same measure, like this is 60 degrees, this is also 60 degrees, we know then those angles are congruent. So we use equations to help us logically, algebraically, okay, and just making statements about numbers. Okay, and then we have inequalities, which I'm going to add that word in here. So these are called inequalities. So if they're not equal, or they're not equalities, then they're inequalities, right? So if two numbers aren't equal, then one has to be bigger than the other, right? Or another way of saying that is, if they're not equal, one has to be smaller than the other in value. So we use inequalities like the greater than sign, the less than sign, and we can add an or equal to in our logic as well. And this is how we express it symbolically. Alright, so now the logic changes about this inequality here versus this equation that we have over here. 2x minus 1, when is this expression, what numbers can we put in for x that makes this expression less than 7, right? So we would have to figure out, okay, well, let's see, what makes 7 first of all? So what number do we double and take away 1? Oh yeah, that was 4. 2 times 4 is 8, take away 1. That's 7. So we know that if x is 4, this is going to equal 7. So then we know that if x is any number that is less than 4, we're always going to get an expression less than 7. So those would be our solutions, right? Like, say 0. 0 is less than 4, so 2 times 0, that's a 0. 0 minus 1, negative 1. Well, yeah, negative 1 in value is less than 7, so that's a solution, right? So the logic changes, and actually there's a whole lot of numbers. 1. 2 times 1 is 2. 2 minus 1 is 1. So 1's less than 7. So that's a solution to this inequality, right? So our logic changes a lot in our solutions when we have inequalities versus just equal to, where it's just one specific value that makes this expression equal to an output. And then also we can look at comparing angle measure. Like, let's say the measure of angle, to make this true, measure of angle ABC, let's call it 90 degrees, it's going to be greater than or equal to the measure of another angle. So let's say greater than, this would have to be some angle that's less than 90, right? Because this has to be larger. So this could be anything less than 90, say 20 degrees, and that would be true. Equal to, they could be equal as well. So if they're both 90 degrees, that would satisfy this inequality as well. Okay? So make sure that you understand that the greater than or equal to, whenever we see an inequality sign opening up or pointing to the right, we're going to read this as greater than, put a little dash under it to kind of do the greater than, and also like an equal sign. Okay, less than pointing to the left. The bigger number is going to go in the opening, the bigger side of your inequality, right? So make sure you understand and we read these signs properly. Okay, so let's get back to this example here. Here's a right triangle. We can since it's a right triangle, and I measured the sides here with GeoGebra, we know that because it's a right triangle, the area of this square plus the area of this square does equal the area of this square, right? And we can use algebra to prove that. But what if we don't have a right triangle? What if, for example, we had an obtuse triangle, right, where the angle's bigger than 90 degrees? What if we had something like this? Okay, now, what about their area? Because as we notice, when we go away from the right triangle here, look at what happens to this side length on our hypotenuse here. It's growing as the angle gets bigger, right? As the angle is bigger than 90, then the distance between these 2 points gets further and further away, right? For a while. Well, yeah, it gets further away when the angle is bigger than 90, right? Because it's a bigger angle. So what happens is the side length gets bigger, so then we have a larger square than we would if we had a 90-degree angle, right? So the c squared value, based off Pythagorean's relationship here, would actually be bigger than the a squared plus the b squared, because as we rotate this point around, the areas here, these side lengths don't change, right? They stay 4 and 5. That's why we use circles and radii to keep congruency, right? So as I rotate this, these areas aren't changing. Their sum is still going to be the same, right? And then this square is growing as the angle gets bigger. So I hope it makes sense that in an obtuse triangle, right, where we have an angle bigger than 90 degrees, then the square of our hypotenuse is going to be bigger than the sum of these two squares, right? Whereas on a 90 degree we know they're equal. That's what Pythagorean's theorem says. What if we have an acute triangle, meaning the angle now, all the angles are less than 90, right? These are all less than 90 degrees. So look what happens to the side length now. Let's go back to 90. Okay, 6.4. And as we shrink the angle, notice the side length gets smaller and smaller. Smaller angle, smaller distance between the 2 points. Okay? So now if we look at the area of this, these areas are not changing here on our 2 legs. So the sum is staying the same, this a squared plus b squared value, right? But now our c squared is getting smaller and smaller. So we know that in an acute triangle, that this relationship, the area of our once hypotenuse, this third side over here, if it's smaller, the angle is smaller than 90 degrees, then this c squared value is going to be less than the sum of the area here and here, right? So that's how we can kind of use Pythagorean's theorem to help us identify what kind of triangle based off side length. Are we going to get an acute, a right, or an obtuse just based off of their sides? We're going to use this relationship to help us just do it, and we don't need to see the segments. And I'll show you what I mean. But let's take a couple notes here. So I'm going to grab my pen. So in an obtuse triangle, that a squared plus b squared, which is just it's just representing the sum of these 2 squares right here, right, based off of our legs. If we know that that sum is less than, so I'm going to use the arrow pointing to the left, right, bigger side over here. If this sum is less than the c squared value, that means that that c squared value is bigger than this sum which would imply then this third side is bigger than the hypotenuse would be if it was a 90-degree angle, right? So if the a squared plus b squared is less than that c squared, this bigger triangle or square, then it's an angle that's bigger than 90 degrees. Right angle, this is our Pythagorean theorem. We know this, that when a squared plus b squared equals c squared, nice writing, huh? A squared plus b squared equals c squared, we have a right triangle relationship, and we're going to use that in the next quest to help us construct squareness, based off of 90-degree angles. And then acute means all the angles like this here, the angles are less than 90 degrees, meaning that this third side is smaller, right? The distance is getting shorter as this angle gets less and less and less. Therefore, that c squared is going to be less than, right? So we know that c squared is going to be less than this a squared plus b squared. Right, the sum of the two squares, areas of their squares. So if we add up the two areas here, and it's greater than, it's bigger than that c squared value, that means that this is going to be an angle that's less than 90 degrees. Okay, so let's use that concept here, and let's answer this question. What type of triangle has sides 6, 4.2, and 9? Okay, so we're going to use, we're going to build this real quick. We're going to take a look at it. But before we do that, let's actually use the algebra side of it. Let's use that relationship a squared plus b squared, see how it compares to that c squared value. So I'm going to just take this problem, put it in here so I can write on it. Okay, so here's what we're really checking. This a squared plus b squared, man, I don't like this little mouse pad, and then we're going to compare it to c squared. So what we can say is we're used to writing the equal. That's how we always check. If they're not equal, then we got to check less than, greater than. So then if we don't know right now if these expressions are equal, so we just put a little question mark above it. It means, are they equal to? And so if they're not, we'll say what it is, less than or greater than. Okay, A and B are going to be always going to be your two shorter sides. The longer side is always going to be our C value. So these can be whatever we want. This could be A, and this could be B, for example. So in this case, we would have 4.2 squared. I'll grab my calculator. So we would have 4.2 squared. We're going to add it to the other shorter side, 6 squared. That's our A squared plus B squared. Right, I'm going to hit enter. So there's the sum of my two sides that are squared, 53.64. And now my longer side over here, which was 9, I'm going to just take 9 squared. We need to know that that's 81. So now we can compare. So the a squared plus b squared, that's 53.64. Right? How's that compare to 81? Well, this expression is definitely less than 81. So in this case, the c squared value is bigger than the a squared plus b squared. Therefore, the angle is going to be bigger than 90 degrees. So this would be obtuse. Okay? Alright. And let's just make this, let's show the visual of y. So we just found out it's going to be obtuse. So when we make this triangle with these three side lengths, the triangle is going to have an angle that's bigger than 90 degrees. Okay, so I'm going to grab my segment tool, but except just the segment tool, I'm going to use the segment with given length tool. So what this does is it allows us to make a segment. So I'm going to put an endpoint on a coordinate point there. And I want this length, I'm going to set it to this first value, 6. And I'm going to hit OK. And what it does is it creates a segment of that value, 6, but the other endpoint that gets made is on, it's like a radius, right? As we rotate the segment around, it just stays that value. So we can actually make any angle we want with these segments. So when you use this tool, it always comes out horizontal by default, and then you can just rotate it around. Keeps that same length. Okay? So I'm going to make another segment here, maybe right here, and I'm going to call it 4.2. So now it's 4.2. Another segment here, I'm going to call it 9. So there's my 3 lengths. What kind of triangle can we make here? Well, I'm going to move this point that's 4.2. Maybe well, we can look at size here and we know which one's 4.2, which one's 6, and which one's 9, I hope. So anyways, I'm going to try to make a triangle here. So I'm going to take my point C, I'm going to map it onto A, and now I can rotate, one of my segments, right? So we can see how we can make a triangle. So now I'm going to take E, and I'm going to put it on this other endpoint, and now I'm going to move this segment around to try to make a triangle. So we can try to make these points fit, but an easier way, if we think about circle construction, and I really want you guys to focus on the circle logic, is look what happens if I draw a circle centered at one of my pivot points here, like this vertex goes out to F, and then we do another one, another radius of our other side length. Well, look at where the 2 circles meet. So if the 2 circles intersect right here, then that probably means that this segment, which is a radius of this circle, right? If I can put it on the intersection point, that other circle touches it, so therefore I can put this point on there as well. And the circle's actually just pinpointed a triangle, a location where those 2 points could map onto, right? And also, notice down here, we have another intersection point, so we could actually move our points to fit right here, and it would be another triangle. You see that? And notice we have this angle in here that looks like it's bigger than 90 degrees. Let's measure it. I use my angle tool there. 122 degrees, right? So the algebra just showed us that we were going to get an obtuse triangle. The geometry, we just constructed that exact triangle that you can make. There were 2 of them, and they're just reflections of each other, right? So they're still congruent. Doesn't matter which one we make. So this is an obtuse triangle. All right, so good luck with that, guys, and let's use Pythagorean's theorem logically now, not just some little formula that we're used to doing. Okay, good luck, guys.